Hi, my name is Stephan Meylan, and my talk today is entitled Child-Directed Listening: How Caregivers' Noisy Channel Inferences Enable Children's Early Verbal Communication. This is joint work with Drs. Ruthie Fouché, Elika Bergelson, and Roger Levy. I'll start by noting that much of the recent progress in understanding how children learn language has emerged under an input-uptake framing of the problem. That is, linking the input that children hear from parents with uptake, or children's consequent language knowledge. Under this framing, theories and models focus on the nature of children's inferences, particularly how children combine their input with inductive biases to produce increasingly sophisticated linguistic behavior. Now, while this has been a highly fruitful approach, the idea I want to explore today is that this is missing a key piece of the language learning puzzle. That is, if we want to take seriously the idea that two-way communication is important for language learning, then we need to listen to Eve Clark and others and think about early language use as a multi-agent process. So we need to characterize not just the inferences of the child learner, but also their adult listener. Today I'll share some work to characterize how adults listen to children's error-riddled speech and robustly recover meaning, or what I'm calling child-directed listening. This is the special ability of adults to hear a child's utterance like, "I want to read," and interpret it as, "I want to read." And with this name, I specifically mean to characterize it as a parallel phenomenon to child-directed speech. That is, not only are there special ways that adults talk to young children, but also special ways that they listen to them. Adult interpretation of children's speech can be thought of as an instance of noisy channel spoken word recognition, so we can use Bayesian inference to model it, as I and others have done for modeling adult word recognition. We can think of spoken word recognition as a process of assigning probabilities to hypotheses about what word was said by the child, in the form of a Bayesian posterior. More specifically, the posterior probability of each possible word candidate identity W, given data D and context C, is the product of the prior probability of the candidate word given the context, and the likelihood, the fit of the observed data to the candidate word. We divide this quantity by some normalizing constant, which reflects the competitiveness of all words in the vocabulary. Returning to weed in our I want to weed example, we can imagine a toy world with two possible candidates for the final word, weed and read. We can then evaluate the candidate word identities in light of their fit to data, and their expectedness in the absence of data. And just to make up some numbers here to cash out this intuition, we expect the prior probability of read to be much higher than that of weed, such that even though the latter is more consistent with the observed data, we assign read a much higher posterior probability. Now, to characterize child-directed listening, we would ideally have records of what children said, coupled with caregiver interpretations. Unfortunately, no such dataset exists, and collecting a large ecologically valid sample is quite difficult. But we realize that we have a second population that has an extremely similar inferential problem to that of the adult caregivers. All the time, developmental language researchers collect corpora and have in-lab annotators create transcripts of adult-child conversations from audio and video recordings. Usually these transcripts include a gloss, or written form approximating what kids said using the adult language. So annotators need to posit the word identity of words in a very similar way to caregivers. So we can look to longitudinal child language development corpora that have phonemic transcriptions and glosses, and rather than think of them as evidence of what children can say, we can think of them as evidence of what adults can recognize as words. For our test cases, we will use the Providence Corpus, a part of the phone bank dataset, which is transcribed with both American English glosses as well as matched phonetic transcriptions for each word. Providence was actually collected with a focus on children's early phonological development, so the annotations are extensive, consistent, and have evaluations of agreement. These transcripts of a few hours of audio and video recordings from the home environments of 6 children were recorded about every 3 weeks, in the longest case from about 12 to 48 months. Now, in the transcripts, we can distinguish between 3 key situations. First, when an annotator finds a word, like in our I want to read example, we call this a communicative success. Now, with the term success, I mean to be a bit glib. It's the annotator's judgment of good enough rather than whether the child's intended message was actually recovered. The second case is when the annotator can phonetically transcribe the speech but cannot determine a canonical adult label for it. We'll call this a communicative failure. For example, one mom asks, "Do you want to put beans in your eggs?" And their child responds, "You make your fet." I don't know what fet means, and more importantly, neither did this annotator, so it's marked as unintelligible. Note we critically exclude a third case where there's a noise in the scene that prevents the annotator from either giving it a gloss or transcribing it phonemically. These tokens are unintelligible, but we don't know why. So that's the phenomenon. How will we model it? For that, let me give an overview of the modeling approach. We take childis and use it to build some predictive language models that can serve as priors in the Bayesian formulation of word recognition that I just presented. We'll also take two priors that don't reflect anything about child language. When we combine each of these priors with the same likelihood function, we get 6 different word recognition models. Then we take the Providence Corpus and do some pre-processing to identify 2 classes of test cases, communicative successes and communicative failures. Now for the evaluation, we're going to use these 2 classes of test cases differently. In the first task, we're going to score the model-based completions against the word identities that annotators found in the communicative successes. In the second task, we will use these models to see if we can predict when annotators give up and flag children's productions as unintelligible. In the paper, there's a third analysis characterizing the contribution of the prior over time, but unfortunately, I won't have time to talk about that today, so I'll refer you to the paper. So for the prior, I'll treat predicting the identity of the word as a masked language modeling task. That is, we're going to provisionally trust the labels for the other words in the utterance and use them to predict the missing word. For the running example of I want to weed, this means masking the final word in the sentence and predicting its identity from the rest of the utterance. For prediction, we'll use BERT. BERT is an example of a transformer, which are extremely powerful neural network models for sequences. BERT has received more than 20,000 citations in 3 years for exactly the reasons that we want to use it as a model here. Specifically because of its transformer architecture, it does a great job at modeling long-distance dependencies, polysemy, and argument structures. There are 2 other favorable characteristics of BERT. First, it's bidirectional. It can make use of preceding and following context, and second, it can be fine-tuned. While the base form is trained on a huge internet-based dataset, it can then be adapted to the statistics of specific smaller training sets by training for a few epochs on that new data. Note that fine-tuning often involves changing the model architecture, for example, adding a layer that serves as a classifier, but in this case, we're going to keep the model architecture the same. We're going to limit the hypotheses about the word identity to a vocabulary of about 8,000 single and bisyllabic words that appear at least once in childis. We include 2 variants of BERT. One, we fine-tune on conversations with children using 80% of English transcripts in childis. This excludes 10% that we use for hyperparameter tuning and 10% for evaluation, and excludes all phone bank datasets, including Providence, which will be our test set. We then query each of these 2 BERT models in 2 ways, once using the immediate utterance plus preceding and following 20 utterances, and once using only the immediate utterance. And to clarify, the utterance context can include what the caregiver has said earlier, not just what the child has said. Crossing child language fitted BERT versus adult off-the-shelf BERT with different access to context yields 4 priors. Then I'm going to introduce 2 additional priors. The childis unigram prior uses normalized word frequencies fitted on children's productions in childis. And finally, the uniform prior is one that assigns equal probability to all 8,000 words in the vocabulary. So what sorts of guesses regarding word identities do these different priors produce? Bringing back the read and fet examples, for read, the child-directed listening plus context model assigns a great deal of mass to see, followed by look and go, while the adult-to-adult model places a much higher probability on read. This is interesting because young children indeed say see and look much more often than they say read to caregivers. Both BERT-based models yield continuations with the appropriate part of speech. Note that these are all verbs. The unigram model, by contrast, does not reflect the context of usage and doesn't limit its predictions to the appropriate part of speech. For the communicative failure, we see both models identify own as the most likely continuation, though the adult model is less peaked and includes some completions that children are unlikely to say, like choice and point. The unigram model makes exactly the same predictions as in the read case, in that it doesn't condition on context. Note for the purposes of this talk, I'm going to use the same likelihood across all models. The point here is to test different priors while leaving the likelihood constant. So I use a standard noisy channel likelihood of exponentiated negative edit distance. The more edits needed to go from the observed data to the citation form for a word, the lower the likelihood term. There's a free scaling parameter beta, which we fit once across all the models. Now I'll show what sorts of guesses the models make, that is, reflecting both prior expectations as well as the phonemic data produced by the child. You can see that this brings read up into the top 4 for both BERT models. This contrasts with the unigram model, which finds closer phonemic matches to the data, but ones that are highly improbable given the rest of the utterance. In the case of communicative failure, this upweights candidates that are similar to the data, though some items are still ranked highly because of their prior probability. And again, the unigram model finds words that are a good fit to the phonemic data, but seem unlikely under the sentence context. Shifting to results, I'll start with task 1, which entails scoring the model completions proposed by the model versus those that were provided by annotators. To quantitatively evaluate which model best captures the words recovered by adults, we look at which model assigns those words the highest probabilities. We use the measure of the average surprisal of the completions, or the negative base 2 log probability, such that a decrease of 1 bit means that the completions are on average twice as probable. That is, lower surprisal indicates a better fit to the annotator decisions. From a set of about 90,000 communicative successes, we evaluate a sample of 1,000 successes from each 6-month time period. When we score the model outputs, we see the following patterns. BERT models are best, followed by the unigram model, and the uniform prior is last. Models with context are better than those without. Among BERT models, those fine-tuned on the child language environment are better than off-the-shelf adult-to-adult models given the same access to context. The takeaway here is fairly intuitive. A model using a longer context and fit to the specifics of child language best replicates the recoveries made by annotators, who again we're thinking of as proxies for caregivers. Now in task 2, we will use all models and try to predict whether a given single syllable segment will be a communicative success or failure. That is, whether it was intelligible and assigned a gloss by the annotator or marked as unintelligible. So in this case, we'll treat communicative success versus failure as a binary outcome. And I'll predict that outcome with a single variable for each model, the posterior entropy over word identities. Entropy here is the weighted sum of the negative log probabilities of all of the candidate word identities. So if the distribution over possible word identities is highly peaked, then this entropy measure will give us a low number, which we think will correspond to a high probability of communicative success. An example of a highly peaked distribution would be that the child-directed listening plus context model puts a great deal of probability mass on a single candidate in the communicative success. Compare this with the communicative failure, where it's more spread out. That is, it's less clear what the correct inference is according to the model. So for this analysis, we have those same 90,000 successes plus another approximately 35,000 failures. And again, we're going to sample 1,000 words from each category for each 6-month age interval. I'll plot this using the ROC, or receiver operating characteristic. The diagonal indicates at-chance performance, and the area under the curve, or AUC, is a succinct measure of classifier quality. Higher is better. And what we can see is that the child-directed listening plus context model best predicts communicative failures. This is to say, the best model depends not just on the literal interpretation of the phoneme string, but on rich expectations and context, and expectations fit specifically to the child language environment. To recap, first, I proposed that adults' inferential abilities, specifically their expectations about children's language use, allowed them to find word meanings in children's highly noisy speech. Then I showed that models of Bayesian spoken word recognition can be used to approximate those inferences. Using annotators as a proxy for caregivers, I showed that a model using the surrounding context and specifically to the child language environment best captures annotators' labels, and that the same model best predicts when annotators find children's speech to be unintelligible. Now on to the consequences. There's a conservative interpretation here that this is just another domain where adults are great at language processing and that we can capture this with a Bayesian ideal observer model. But I think there are plenty of more exciting implications for language learning. In general, there are 2 broad categories of implications for this work. First, there are methodological ones about what it means to evaluate lexical knowledge on the basis of what children say, or per this talk, what adults think children say. And second, there are implications for the language learning process itself. How might the problem of language acquisition be different in light of these rich caregiver abilities? But to learn more, you'll have to read the paper. And with that, I want to thank my co-authors, the creators and annotators of the Providence Corpus, the families in Childus, and my funding source. And thank you for listening.